Hello, students, and welcome to the 14th lecture on particle physics. In the 13th lecture, we have introduced parity. We also talked about the intrinsic parity and orbital parity. And today we shall move forward and we will talk more on the parity operation. Now, a system is said to be invariant under parity if the Hamiltonian remains unchanged by this operation. This is what I had told you in the last lecture also, that if the Hamiltonian commutes with the parity operator, then the quantum number associated with the parity operator is a conserved quantum number. And that means we say that parity is conserved for such process described by the Hamiltonian, say H. Now, this is true in the case of strong interaction and electromagnetic interaction processes, but in the case of weak interaction, it gets violated. The mathematically, we are going to express this in the following way, that we have a Hamiltonian which is depending upon r1 prime, r2 prime, rn prime, and p is the operator. Then r1 prime, r2 prime, etc. will change to minus r1 prime minus r2 prime, etc. And if it gives the same Hamiltonian as h r1 prime, r2 prime, rn prime, then we say that quantum number associated with the parity operator is a good quantum number. Now, the Hamiltonian for the electromagnetic and strong interactions commute with the parity operator, while it is violated in the case of weak interaction. And this is how we can represent the condition that the Hamiltonian for the electromagnetic and in weak strong interactions, they commute with the parity operator, while in the case of weak interaction, Hamiltonian does not commute with the parity operator, and therefore quantum number associated with the parity operator in the case of weak interaction is not a good quantum number, is not a conserved quantum number, and we say that parity gets violated in the weak interaction. Now let us just recall again the discussion on intrinsic parity. Suppose we consider a particle and introduce a parity operator defined by p psi rt is equal to pa psi of minus rt, where A stands for the particle like electron, proton, neutron, whatever you talk about, and Pa is the constant phase factor. Now, what we had seen that if we repeat this parity operation, we should get the original state, and then Pa square can be either plus 1, should be 1, and Pa will be either plus 1 or minus 1. Plus 1 corresponds to even parity and minus 1 corresponds to odd parity. Now, what we did, we wrote the wave function, which is an eigenfunction of momenta on the last term in this way, and then said that it is equivalent to replacing, instead of r by minus r, if you replace p by minus p, then this is also the same expression. Now, if the particle is at absolute rest, then the parity possessed by the particle, what we call it as intrinsic parity, and today we shall talk more about it. And then for a system consisting of many particles, this is defined as p1. This is a multiplicative quantum number, and therefore parity of one times parity of other times intrinsic parity of the third one, and so on. That will be the net parity of the system. Now let us talk about the parity of leptons and baryons. Now, what we have discussed, that parity is not a good quantum number in weak interaction. Therefore, we cannot determine the parity of leptons and baryons through the weak interaction processes. That means we are left with a strong interaction process and electromagnetic interaction process. Then leptons do not take part in strong interaction. Therefore, we are only left with one option for the leptons, that is the electromagnetic interaction process. But for the baryons, we have two choices, either to determine in a strong interaction process or through electromagnetic interaction process. But the most important point we have to remember that we have to conserve lepton number independently for the electrons, for the muons, and for the tauons, and then the baryon number. Now, if I want to determine the parity of electron and take any example like E minus plus P going to E minus plus P, then this will be parity of electron times parity of proton. This will be some minus 1 to the power L, parity of electron times parity of proton. Now you see these two will cancel out. Then if I talk about E minus E plus going to 2 photons, then we have parity of electron, parity of positron. This is something, but whatever number we get, either minus 1 or plus 1, we cannot determine the parity of either electron or parity of independently of positron. Therefore, since electron lepton number, or similarly you can talk about the muon lepton number, they are independently conserved. Therefore, you will have to have either one muon here and one muon here, or you will have to have mu minus and mu plus like this. Like if I consider the process E plus E minus going to mu minus mu plus. Therefore, all the time that you talk about, you will have either one lepton, one anti-lepton of the same time, or one lepton and the same lepton on the right hand side to conserve lepton number quantum law. And therefore, there is no way to determine the parity of leptons. Similarly, if we talk about the parity of baryons, then there also baryon number is conserved, and you cannot write a reaction where you have only one baryon in the state. Like if I talk about pi minus deuteron scattering, where we have two neutrons in the final state, you see there are two neutrons, and therefore when I will write Pn times Pn, whether this is minus 1 or plus 1, this will give me 1. And similarly, you can think of any other reaction, P plus pi plus going to pi plus plus P, or pi minus P going to pi 0 n. You take any strong, these are all strong interaction processes, or electromagnetic interaction process, gamma plus P going to gamma plus P, electromagnetic interaction process. What you will realize that here also we have at least two baryons. Therefore, there is no way to determine the parity of leptons and parity of baryons. We assign the parity or intrinsic parity of these particles by hand. And traditionally, since we call electron and proton to be particles, because electron was the first particle which was discovered by J.J. Thomson, and then proton was discovered by Rutherford, therefore we assign plus 1 parity to electron and plus 1 parity to the proton, neutron, etc. And similarly, if we assign plus 1 parity to the electron, we assign plus 1 parity to the muon, tauon. But there is a catch here, that if we are assigning plus 1 parity to the electron, then quantum field theory demands that, to be consistent with Dirac equation, this product should be equal to minus 1. Then what does that mean? That we have to assign parity of positron to be opposite to that of the electron. Therefore, parity of positron is minus 1 by hand, and parity of electron is plus 1. That means you can equally say that, why not assign parity of positron to be equal to plus 1? You can do that, but in that case, we will have to put parity of electron to be -1. Or if I say that parity of antiproton is +1, then parity of proton will be -1. But traditionally, since we call electron, proton, neutron as particles, we assign +1 parity to these particles and -1 parity, intrinsic parity, to the antiparticles. Therefore, to anti-lambda or anti-sigma or anti-proton or positron or mu plus, we assign intrinsic parity to be -1, and to the particles we assign parity to be +1. Therefore, what to summarize, we have only the electromagnetic and strong interaction processes to determine the parity of particles, and since the leptons do not participate in strong interaction, therefore we have only one choice, that means consider the electromagnetic interaction processes, while for baryons we have both the options. Either we can determine it through electromagnetic interaction process or through strong interaction processes. For example, here I have taken the various reactions, and here always you will find that either we have one electron and one electron on the left hand side, right hand side, one proton baryon number here and one baryon number here. Therefore, there is no way to determine the parity of these particles, and we assign the intrinsic parity of these particles by hand, and this is +1 for electron, muon, tauon, proton, lambda, sigma, etc., and -1 for antiparticles, that is the demand from the Dirac theory. And therefore, in the case of leptons and baryons, we cannot determine the parity and we assign by hand. But this is not true in the case of mesons, or we can determine the parity of photon, etc. Suppose I am taking the case of neutral pion. This is a very interesting example where a pi0 is decaying at rest. When it is decaying at rest, then its 3 momenta is 0. And to conserve 3 momenta, both these photons have to travel exactly in the opposite direction with the same magnitude of the momentum. And say this photon has got polarization vector epsilon 1, this photon has got the polarization vector epsilon 2. Therefore, the vectors those are available to us in this process is the momentum and these two polarization vectors. Now, that means the wave function that we will talk about, or the amplitude that we will talk about for this process, will be either k dot epsilon 1 or k dot epsilon 2 or epsilon 1 dot epsilon 2 or epsilon 1 cross epsilon 2 dot k or k dot epsilon 1 cross epsilon 2. These are the only 4 choices available at our disposal. That with these 3 vectors we can constitute the following 4 scalars. That will, the amplitude should be proportional to these quantities, and then we have to see that whether all these 4 terms are going to survive. The answer is no, because what we are talking about is the real photons, 2 photons going exactly in the opposite direction, and we know that the real photons are transverse in nature. The polarization vector is perpendicular to the direction of the propagation of the particle, and therefore these 2 guys, they are not going to contribute. We are left with only these 2 fellows. Now, there is again an important catch. We know that the intrinsic parity of photon is odd. We have seen that epsilon changes to minus epsilon. Therefore, here we are seeing that epsilon 1 dot epsilon 2 under parity operation will not change sign, because both epsilon 1 and epsilon 2, they are going to change sign. While if we consider the second term, epsilon 1 cross epsilon 2 dot k, then what we realize that epsilon 1 cross epsilon 2 is not going to change sign. But since k is changing sign, therefore overall there is a change of sign. Change of sign here under parity operation, while there is no change of sign. And we have learned that if there is no change of sign, then that quantity will be scalar, while if there is a change of sign under parity operation, then the quantity will be a pseudo scalar. While under proper Lorentz transformation, they are transforming in the same way. Therefore, one is scalar, another is pseudo scalar. One is changing sign, another is not changing sign. Both cannot be true. Only one of them has to be true, because parity is conserved in electromagnetic interaction. If it is changing sign, it is odd, it will remain odd, or if it is even, it will remain even. Therefore, the important point is either the wave function will be proportional to epsilon 1 dot epsilon 2, or the wave function will be proportional to epsilon 1 cross epsilon 2 dot k. Now, who is going to decide? The answer to that is experiments are going to decide what should be the wave function. Therefore, this is what we have discussed, that we have epsilon 1 dot epsilon 2 either, or epsilon 1 cross epsilon 2 dot k. Now, a and b here are the constants, and phi is the angle between the planes of polarization. Therefore, if wave functions are proportional to, say, cos phi here and sin phi here, then that means the intensity will be proportional to cos square phi and sin square phi. Now, it is difficult by measuring the polarization of the photons to determine the parity of pi 0. But what one does, one consider this process, real process, where a gamma is giving rise to E plus E minus, and this gamma is also giving rise to E plus E minus. And by looking at this reaction, people have determined the parity of pi 0 by finding out that the results are consistent if the wave function is proportional to sin phi. That means the term that is proportional to epsilon 1 cross epsilon 2 dot k. That means the quantity is pseudo-scalar. And therefore, we say that the parity of pi 0 is odd. Next, this is what I have explained. Now, the next very interesting example is of parity of the charged pion. And parity of the charged pion is determined in the reaction pi minus plus scattering on the deuterium target, where you have the two neutrons in the final state. Now, this is an interesting example where deuterium is a proton-neutron bound system which stays 96% of the time in the atomic S state. Let me repeat it, that deuteron is a bound proton-neutron system which stays 96% of the time in S state and 4% of the time in D state. Again, after S, P comes in the atomic physics, but S will have L equal to 0, while P will have L equal to 1, as we have discussed earlier. S is equal to 0 will correspond to even parity, L is equal to 1 will correspond to odd parity. It cannot have both the parities. Therefore, the parities, to be consistent with parity and to explain the quadrupole moment of the deuteron, because we know that deuteron has a finite quadrupole moment. Therefore, it cannot only be explained by L equal to 0 state. We need an admixture of state, and therefore the wave function has the S component as well as the D component. But the contribution from D is very small. It is only with 4% we are able to explain the result, and therefore we are talking about a deuteron system. The parity of deuteron, since it stays in, it is defined as minus 1 to the power L, parity of proton times the parity of neutron, as the deuteron is made up of proton neutron bound system. And then we have seen that we assign by hand the parity of proton and parity of neutron, the intrinsic parities. Even if you say that we have defined, we have taken by hand these numbers, why not take it minus 1? Okay, fine, you may take it, but parity of proton times intrinsic parity of neutron, they will still give you plus 1. Therefore, this guy, this is going to give you plus 1. And then since it is staying 96% of the time in S state, which is L equal to 0 state, therefore parity of deuteron is even. This is parity of deuteron is minus 1 to the power 0, that is plus 1. Okay. Remember, we have discussed while discussing isotopic spin that deuteron is an isosinglet state, because we don't have diproton and dineutron system. One more property we are learning for the deuterons, that deuterons have got intrinsic parity. Now, the parity of pion times parity of deuteron, this will be equal to minus 1 to the power L, the relative orbital state for the two neutrons. Parity of, let us have a pion absorption in the deuteron. Say the relative orbital state is minus 1 to the power L. As we have discussed that for atomic systems, we have to consider orbital parity. Therefore, we have minus 1 to the power L parity of pion times parity of deuteron times minus 1 to the power L parity of neutron times parity of neutron. Now, this is plus 1. It's fine. Then we have on the left hand side this equal to plus 1. Good. But the other important point is this pion absorption in the deuteron, this takes place in the atomic S state. This is the slow absorption of pions in the deuteron, and it is ensured that this absorption takes place in the atomic S state, and therefore L equal to 0 for slow pions. And that means what ultimately we have, the parity of pion is equal to minus 1 to the power L. This L, if we determine for these two neutrons, the relative orbital angular momentum states for the two neutrons, then we will be able to tell about the parity of pion. And this is how the parity of pion was determined. Now let us start the discussion. This is what I am talking about. A pion getting absorbed by the deuteron, and we have two neutrons in the final state, and we are talking about a deuteron which is a spin 1 system, and as I am telling you that 96% of the time a deuteron lives in L equal to 0 state, S state. Therefore, the total angular momentum is 1 here. Here, the total angular momentum of pion is a spinless particle. And therefore, the total angular momentum of the initial state, as you can see, this will be equal to 1, as pion is being absorbed in the atomic S state. Therefore, S pi is 0, SD is equal to 1, while LD is 0, and absorption is also taking place in the atomic S state. Therefore, total J in the initial state is 1, and the same should be the total J in the final state. Now, what we know, that means we have to be very clear about it, that the total angular momentum of the initial state is 1, because this is S pi is 0, this S pi is 1, and L is 0. Therefore, whatever J you are getting is from this guy. And therefore, Ji is 1. The angular momentum of the initial state is 1. And exact conservation law tells us that the total angular momentum of the final state then should also be 1. Now, if this has to be 1, what other things that we know about the two neutrons in the final state? That neutrons are fermions, they have got a spin half. And when you have two spin half objects, these two objects can give you total spin 1 or total spin 0. This total spin 1 is a symmetric state, because 1 can have a projection plus 1, 1 can have a projection 0, 1 can have a projection minus 1, while 0 that we are talking about has only one projection, that is 0. Now we have learned while discussing isotopic spin that plus 1 I can only get when both the projections will be plus half plus half. This will give me plus 1. That means this is half, 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 1, and that is giving me half plus half and half plus half. You see, this Clebsch-Gordon from the Clebsch-Gordon table is 1. Then that means this is half plus half state. This is half plus half state. That means for 1 plus 1, both the neutrons should be in a spin up state. Now let us talk about 1, 0. This 0 we can achieve when the spin projection of the first neutron is plus half and the second neutron is minus half, while spin projection of, in the other case, spin projection of first neutron is minus half and the second neutron is plus half. That means 1, 0 I can achieve by half, half, 1, plus half, minus half, 0. This is half plus half, then half minus half, then plus half minus half, half plus half, 1, 0, and this time this will be half minus half times half plus half. Now the Clebsch-Gordon for this is 1 by root 2. Clebsch-Gordon for this is also 1 by root 2. Therefore, what we are getting is that this is 1 by root 2 particle which is in state 1 is in spin up state, 2 is in a spin down state, and this is in a spin down state, and this is in a spin up state. Therefore, if I interchange the position of these two particles, then what we realize, nothing is going to change. Therefore, this is a symmetric state, like this was a symmetric state. Similarly, if I talk about 1 minus 1, this we can achieve if we have half minus half, half minus half. This is giving me 1 minus 1. And that means both the particles are in the spin down states. This is in a spin down state, as well as the other neutron is also in a spin down state. But if I interchange these two, nothing is going to happen. Therefore, this is a symmetric state. Therefore, with 1 plus 1, 1, 0 and 1 minus 1, we are getting symmetric states. But what about this 0, 0? If I put here this 0, then here there will be a change. This will be 0 and this will be 0. See here, the change is only here. Other options will remain the same. But what this change brings, this value of Clebsch-Gordon coefficient is plus 1 by root 2, while this value of Clebsch-Gordon coefficient is minus 1 by root 2. Therefore, the state that you will get will be 1 by root 2 up down minus down up. Now you see, if you interchange the position of these two particles, you will pick up a negative sign. Therefore, you are picking up a negative sign when you have the state 0, 0. Therefore, this is an anti-symmetric state, while the other three are symmetric states. So therefore, we have to consider these facts into account, that we have two neutrons, both the neutrons are spin half particles, total angular momentum is 1, while L we don't know on the right hand side. And also presently what we are seeing, that if we have two spin half particles, then we have four states, three are symmetric spin states and one is anti-symmetric state. We will take care of that into account. See, these are the different states that I have shown, and using them we can say that if we have these four states, therefore this state is C, 0, 0 is an anti-symmetric state, while these are symmetric states. Therefore, overall symmetry you can determine by minus 1 to the power s plus 1. You see, when s is 1, this is a symmetric state, the last three. When s is 0, this is an anti-symmetric state. Therefore, overall symmetry you can take care of by introducing a factor of minus 1 to the power s plus 1. Therefore, minus 1 to the power s plus 1 will determine the symmetry. Then we have the factor of minus 1 to the power L from the relative orientations or by angular momentum orientation of two neutrons. Therefore, overall symmetry will be determined by minus 1 to the power L plus S plus 1. Therefore, when we have two neutrons in the final state, overall symmetry will be determined by minus 1 to the power L plus S plus 1, where S plus 1 is coming from spin and L is coming from the orbital parity part. Now, what is the important point? That the initial angular momentum is 1. Therefore, final angular momentum has to be 1. Now, we have to be careful that S can be only 1 or 0, and overall this quantity, since we are talking about two neutrons, these two neutrons are fermions, and fermions are described by anti-symmetric wave function. Therefore, L plus S plus 1 should be odd. Therefore, the anti-symmetry of the wave function requires that L plus S plus 1 should be odd, and total angular momentum requirement is that GF is equal to 1. Therefore, we have S is equal to 0 or S is equal to 1. And then we have the different possibilities of L. L can be 0, L can be 1, L can be 2, L can be 3, any number like that. But the important point is the final GF should be equal to 1. Now let us take one by one. If S is 0, L is 0, it cannot give me 1. If S is 0 and L is 1, then J is 1. But since the overall wave function has to be odd, therefore we cannot consider this also, because if S is 0 and L is 1, then this is minus 1 to the power 2 and this is becoming symmetric. Now let us take another one. S is 1 as L is 0, then J is 1, it's fine. But again, L plus S plus 1 has to be odd. That means L plus S has to be even, and therefore S is 0 and L is 1 is not allowed, it is odd. Now let us take another one. S is 1 and L is 1. The total J for S is equal to 1, L equal to 1, we can get 0, 1, 2. Everything is fine. This is 1 and L plus S is giving me 1. This is an overall, what we are finding out, that L plus S plus 1, 1, 1, 1, minus 1 to the power cube. This is odd. We required the wave function to be anti-symmetric in nature. Therefore, wave function is coming anti-symmetric. L is 1, S is 1. This is one option. Let us go to another option. S is 1 and L is 2. Then what will happen if S is 1 and L is 2? Then again you see this will become symmetric, L plus S plus 1, while we required anti-symmetric. Therefore, what you will find out that only option is when your L is 1, S is 1, that will give you GF1, and that will also ensure that L plus 1 S plus L plus S plus 1 is odd, such that the total wave function is anti-symmetric. Therefore, this is how we arrived at the result that the minus 1 to the power L with the two neutrons, and here we had the parity of the pion. Since this was plus 1, this L is equal to 1 is the only option. The parity of pion is odd. Let us stop here and we shall start the discussion from this place about the parity of the particles. Thank you.